Welcome back, everybody. We are looking at machines and efficiency. So let me go over a review of mechanical advantage as we talked about in machines, and then teach the very easy concept of efficiency. So let's look at a mechanical advantage. If you remember, if you had a pulley, block and tackle that had two strings attached to the weight, we said that it had a mechanical advantage of 2. Okay, because it's twice as easy because you're having length of string 2 times instead of 1. As this is lifted up 1 unit, 2 lengths of string are lifted up 1 unit. So you have twice the distance, so half the mass. Remember that work is going to be equal to force times distance. And a lot of these machines you're going to see have this FD on each side. So you have input work and output work. And so you have input force, input distance equals output force, output distance. So a mechanical advantage of a ramp, remember, is the length of the ramp divided by the height. So we want this number to be a positive number. So a mechanical advantage of, say, 2 would be if this were twice the length of this. A mechanical advantage of 6 would be when this was 6 times the height. Okay, so every machine is slightly different, but you're always going to have this kind of idea where you're going to have the force input, that's what you put in, times the distance, force distance, equals the output force. So the force out, that's what you're lifting, times the distance out. Okay, so if you can make your force low by making what you pull longer, like a longer string or going up a ramp longer, then you can have that same output force, which would be high, and the short distance. So like a lever, if you have a fulcrum here, and I have a lever and I have a very long arm on my side and a little bit of force, I can, with a little bit of distance, push a large force. That's what a fulcrum does. So essentially you're making use of force distance. You're putting in a little force and getting a big force out. You're putting in a lot of distance for a short distance there. Okay, so even a hammer pulling a nail, you're going to have a very small, if this is the head of the hammer, okay, if that's the head of the hammer, you're going to have a very small distance here, very, very small, but a longer distance here with the hammer as you try to pull the nail. It's easier than trying to pull the nail out with your fingers. All right, so let's look at a few of these. Oh, I meant to say mechanical advantage. Mechanical advantage has to do with distance. You have something called ideal mechanical advantage, which is just like if there were no friction at all, just the ideal. Well, the ideal is going to be just comparing the two distances. So you would say that the ideal would be the distance in, okay, how much you have to pull, divided by the distance out, what's actually going to happen. So the distance in would be your distance of your crowbar, and then the distance out is the little distance from the nail to the fulcrum. Okay, so that is ideal. The real world, though, there is force involved, and so you have something called actual mechanical advantage, and the actual mechanical has to do with force. All right, so when you do output, you want that to have the big one would be your output. So the force out and the force in. So you want to put a little bit of force in, so you want your number less. You want this to be equal to greater than 1. So you want the force that you're exerting to be higher than the force you put in. If you're putting in more force than you're getting, you shouldn't use a machine at all. A machine's only an advantage if you can put a small force in at a great distance and get a big force out at a little distance, like this. So ideal talks about distance, and you want a big number. You want the distance you put to be big so that your force is little. So you're going to have it over top. For actual, it's the output force divided by the input force. Okay, hold on, I have to plug in my machine. Okay. Excuse you, I was dying. All right, so let's look at this first one. A windmill uses sails blown by the wind to turn an axle that allows a grindstone to grind corn into meal with a force of 90 newtons. Okay, so I've got a force for the wheel, for the grindstone, at 90. The windmill has sails with a radius of 6 meters blown by the wind that exerts a force of 15 newtons on the sail. So I've got less force that the wind blows and a greater force that's grinding the corn. And so that's good. That would be a mechanical advantage. The axle of the grindstone has a radius of 0.5. So you have 90 force is going to be your output force. 15 newtons will be your input force. So you have a big output force, a little input force. So you already know that the actual mechanical advantage is going to be 90 over 15. And then you've got some distances. You've got a 6 meter radius is the input distance. That's the one that's on the outside. That's the input. The wind is inputting and then it's grinding on the inside. So this is 6 meters. And then the radius of the grindstone is a half a meter. Okay, so you've got, let's just label these. This is output. This is output force. This is input force. This is input distance. And this is output distance. Right, so what do we ask for? What is the ideal mechanical advantage of the wheel? Well, those are distances. So the ideal mechanical advantage are just distances. So we want to say you've got 6. 6 is your input distance divided by 0.5 is your output distance. Okay, so 6 divided by 0.5, that's 12. So you have an ideal mechanical advantage of 12. B says, what is the actual mechanical advantage of the wheel? Well, those are forces. So you want to know how much force are you getting out divided by how much force are you getting in. Well, how much force you're getting out is the cornmeal being ground, so that's 90 divided by 15. So 90 divided by 15 is 6. And now they're asking for the efficiency. And efficiency is very easy. You just want the actual mechanical advantage divided by the ideal mechanical advantage. So you have actual mechanical advantage divided by ideal mechanical advantage. That's your efficiency, and it's going to be in percent. So you're going to have a decimal that you then multiply by 100%, giving you a percentage. So your actual is 6. Your ideal is 12. So 6 divided by 2, or 12, equals 0.5, and 0.5 times 100% equals 50%. Okay, so you're getting 50% of the energy that the wind is blowing in this actual machine. So it's easier, and certainly easy using the wind than it is grinding with your hands. But in terms of this whole machine, if you weigh the output and the input, you'll see that some machines are inefficient, some are very efficient. I think the most efficient machine I've ever heard is a bicycle. It's seriously efficient. You're using almost all of your energy to go somewhere rather than just simply push it around. Something like a fireplace or a heater probably would get very low percent, maybe 10% of the energy that you're burning is actually going to heating your house. The rest of it is going up the chimney. So efficiency is this idea of how much do you have, how much are you getting, depending on how much you're putting in. So let's look at this next one. This is a harder one. I don't like these. This is a second class fulcrum where, like if you were to take the fulcrum, you've got something like this. Let me think. Here's, you're pulling, yeah. So you're pulling up, and here's your weight. So it's just very low. I mean, this is hard. there's not a lot of energy from this, but this is how your arm is designed. You just have to work very hard for a little bit. It's not in the way. Like if you had a fulcrum in the way, it might be a little more efficient, but you'd look really funny. So in any case, let's look. You've got a waitress. We're trying to find out how many newtons of force is she exerting on her bicep in order to lift a tray. So she's got a large tray here in her hand. You've got a length of arm. Let's see, it's 30 centimeters arm from her hand to her elbow. From her elbow joint to her bicep muscle is 5 centimeters. Okay, so this is, what is she inputting? Here's her input force. That's what we're trying to find. How much force must her biceps? So the input, the force of N is what we're trying to find. The distance N is the small distance between her bicep and her elbow. The distance out is going to be this length between her hand and her elbow. This is the length of her arm. And the force out is actually her hand holding up a tray. So her force out will be whatever's in the tray. So we need to put these all together. Remember, you're going to have typical force in times distance in equals force out, distance out. Okay. All of your math theories were essentially the same of all the simple machines that you found, where you have, N1T1 equals N2T2, or F1D1 equals F2D2. This is what the math you found the other day. All right, so let's find out. We want force in, so we want this. So we want something like this. We want the output force, which is what she's carrying, the output distance, which is her arm, divided by the input distance, which is from her bicep muscle to the elbow. All right, so how much is she carrying? She's carrying a 5 Newton tray plus 12 3.5 Newton plates. So that's her force out. We multiply that by the distance out, which is 30 centimeters. Let's go ahead and put that into meters. 30 centimeters is going to be 0.3 meters divided by the distance in, which is this. So 5 centimeters is going to be 0.05 meters. So what is that? You're going to have 12 times 3.5 plus 5 equals times 0.3 equals divided by 0.05 equals. So I get her force equals 282 newtons. I'd hate for that to be on a test. That would scare me to death. It's not really hard. I just don't like these kind of fulcrums. They're scary. All right, this one's awful. This one uses a little bit of trig. Trig's never gone past baby trig. If you remember, we're basically just using Pythagoras' theorem and sine, cosine, and tangent functions, and that's all. We did learn how to do an arctangent or an inverse tangent, second function tangent, or second function sine, cosine, tangent in order to find the angle, and we're going to need that today. All right, so when building the pyramids, the ancient Egyptians were able to raise large stones to very great heights by using inclines. If the incline has an ideal mechanical advantage of 4 and the pyramid is 15 tall, how much of an angle would the incline need to be for the order for Egyptian builder to reach the top? It's very scary. Essentially, you've got an, let's say this is an obelisk or a pyramid or whatever, and here is your incline. You're going to, first of all, we have to find out what this length is, and we know that it's 15 meters tall. We already know that because that's what's tall, so that's going to be there. And now we're going to try to find this angle. All right. Well, if you remember ideal has to do with distances. So an ideal mechanical advantage, okay, an ideal mechanical advantage is going to be the distance in, so the distance you have to walk with the block, divided by the distance that you travel with the block. Okay, so the distance out. All right, so the distance in divided by the distance out. Well, the distance out is how much height you're getting. So this is going to be 15. If your ideal mechanical advantage is 4, how much is this ramp? So that would be this. So I'm going to get rid of this 15. 15 times 4 is 60. So the distance in is going to be 60, and the height's going to be 15. So now I know I've got opposite over hypotenuse, that's sine. So I'm going to have the sine of theta equals 15 over 60. Okay, so 15 divided by 60. Okay, that equals 0.25. And now I know that the sine of theta is 0.25, but what's theta? You're going to have to put 0.25 in your calculator and then do an inverse tangent, a second function tangent. So second function, or not tangent, sine, because I've been using sine. Sine. And I've got theta equals 14.48 degrees. Okay, 14.5 degrees is how much the angle would be in order to make a ramp to get to the top of that pyramid. That's the idea. Math, math, math. Last one. The Ramseys are moving to a new town, so they have called in the Acme Moving Company to take care of their furniture. Debbie, one of the movers, slides the Ramseys 2,200 Newton china cabinet up a 6 meter long ramp. She must be one strong mover. All right, so if I've got a 6 meter long, and which is 1 meter off the ground, so remember this is a mechanical advantage of 6. This is 6, this is 1, right? She's pushing a china cabinet up. It weighs 2,200. And she's pushing with what? Okay, we'll have to find out. It's in the B part. She's pushing with 500 newtons. Okay, so her push is 500 newtons, and she's pushing a 2,200 newton up. All right, so let's look and see what the question is. What is the ideal mechanical advantage? All right, we just did ideal. Ideal mechanical advantage has distances in it. All right, so this is going to be distance in, which is our long 6, divided by the distance out. So 6 divided by 1 will give you a ideal mechanical advantage of 6. Okay. What is her actual mechanical advantage? Actual mechanical advantage is going to be force. So how much force is coming out? So, you know, what's actually being pushed, the force of the china cabinet divided by the force that she's pushing. Okay, because you always want it to be a big number. You don't want to push more than the weight. Okay, so you're going to have the weight of the china cabinet, and then you're pushing less, and this is going to give a number bigger than 1. So output force is going to be 2,200 newtons. Input force is 500 newtons. Okay, so that is 4.4. Okay, so number A is 6, B is 4.4. And there's no units here. It's just a mechanical advantage of 4.4. It's 4.4 times easier to push it up a ramp than it is to lug it or hoist it. And then the last one, what's the efficiency? If you recall, efficiency is actual mechanical advantage over ideal mechanical advantage. So your actual mechanical advantage is 4.4, and your ideal mechanical advantage is 6. Okay, so that gives you 0.73 times 100%, gives you 73%. So dragging it up that ramp is a 73% of her energy is actually used. She's only wasting a little bit of energy doing it. Most of the energy she's pushing with is actually getting it up. There's friction on the ramp between the wood. I'm sure she's tearing up that china cabinet pretty nice, but in any case, it's 73% efficient. that would go here. Keep going, keep going.